Hello everybody, welcome to my tutorial. In this tutorial I will teach you how to design supersonic conical gas targets suitable for wake-field accelerators and simulate their fluid dynamics using Ansys Fluent. Although this is a very specific example of nozzle which are used in wake-field accelerators, you can adjust the geometry so that you can simulate, for instance, nozzles that are suitable for rockets and so on. In general, the nozzle used in wake-field accelerators are designed so that the gas density profile above the outlet at a certain height is as uniform as possible, also called the flat top profile. Because of this requirement, the nozzle's geometry must meet certain constraints which are shown on this page. I will not read them, but implement them directly when we draw the geometry. If you want to read more about designing this kind of nozzles, here you have two references. They will explain why certain choices are made. So, for instance, the ratio between inlet and outlet, why should we have a still region, and so on. Here I show a drawing of such a nozzle, so a supersonic nozzle. And here you can see a picture of a manufactured nozzle. In the simulation, I will ignore the wall of the nozzle, which in the simulation is considered perfectly smooth and adiabatic, and simulate the fluid dynamics only through the interior of the nozzle. So the wall in the simulation is considered infinitely thin. Of course, you can consider the wall simulation in the wall properties in the simulation if you really need it, but they are unnecessary for our purposes. All right, let's get started. First, let's open the Ansys workbench, which contains the many workflows, and depending on what license you have, you can have many more options here. So to start the simulation, first thing first, drag and drop fluid flow with Fluent right here, and you can give it here a name. Let's say to the Axis, give it as a meaningful name, so that if you want to check the simulation again after a while, you can easily recognize what is there. Otherwise, it's easy to forget. All right. From here you can change the units if you really want, so you can have metric, all sorts of units, and you can have imperial units, engineering units, and so on. We will use metric in this tutorial. The workflow is as follows. So first you will draw the geometry right here, then you'll go to the next step, you'll mesh it, so you'll create cells, and so the next step will be to prepare the simulation and run it, and the last will be to extract the data and prepare it in a presentation form. Okay, so to draw the geometry, you have multiple options. So if you right click on this one, you have two programs to use, so design modeler, space claim, or if you want to do it in another using other CAD program, you can do it externally and import it using this this option. We will use design modeler. I'm used with this program, so I will use it for this tutorial, but feel free to use whatever you want. So just click on design modeler and the program will start. click on XY plane, then right click on the screen, look out to see the the XY plane. Since it will be just a 2D geometry, it will be done in this plane. Now if you are using mouse scroll, you can zoom in. It's better to zoom in now because the geometry will be very small, and you want to see it properly. From units, we will not use meter, we will use millimeter since the nozzle is very small. So again, I scroll until I see about 10-20 millimeters or something like this. Here you can see the scale on the bottom of the screen. Try to actually don't try, you have to learn a good habit. When you are designing the nozzle or designing the gas target, try to have the direction of the flow in X direction and the transverse direction will be Y. Even if it's 3D, try to do it the same. On long term, it's easier. So right now we have to sketch the geometry. So the easiest will be to just do it step by step. So because of the symmetry, we will not draw the entire cross section through the middle of the nozzle. We will need just half. So we want this nozzle. So we start from here. If you click, and if you are vertical, you will see a V there. So that tells you that the line is vertical. If it's not, it disappears. So it's easier in this way to draw it. So click on this one, and we want the entrance of the nozzle to be 2 millimeters. So that means half will be 1 millimeter. So if you go to dimensions, and you can use general or vertical options. So I use general. Sometimes it fails to recognize what you want, so that's why you need to use these ones. In this case, it shouldn't be a problem. Click like this, and let's say 1 millimeter. Okay, it looks very small there, so it's hard to see. Right click on the screen, look out, and it will increase. Maybe it's a bit too much. Alrighty. And now let's draw the next part. So, okay, sketching line, another one like this. So again, you see there an edge. If it's horizontal, if it's not, it disappears. So let's do like this, and again dimensions, horizontal. Oops. And let's say I want about 5 millimeters. So the length of this section should be 10 centimeters. Is the steel chamber, which is quite important to stabilize the flow. So let's say I will choose it 5. Enter, and again I use the scroll to change this part. Again, if you don't, if you want to move the geometry to see it better, you can click here and move it like this. Okay. Now let's draw the convergent part. Draw line. Okay. Okay, so I made a mistake. Okay. So can use this one and delete. Okay, go back, line, and we'll draw a line like this in angle. You don't really have to define it now. And this will define, so this is going in the throat region. So the throat or the inlet, so the inlet is measured at the throat. We want to be 0.5 millimeters. So that means in this case, since it's only half of the cross section, it should be 0.25. So we will use again dimensions and vertical. Click on this one, click on axis, and let's put it here, V3, and that's 0.25. Alrighty, and now let's define the angle between this line and the main axis. So for that one, you will use the angle. Click on line, click on axis. And this angle, I don't really like it. I want to show the angle directly from these two parts. So right now, right click and choose alternate angle. And this is the angle that I want. There will be multiple angles, so keep right click and alternate angle until you find the angle that is shown properly for you. Click on this one, A4, so this one we want about 20 degrees. All right, and now let's draw the throat. So draw line, throat. The throat again has to be has to have a certain length. If it's too short, it's not good for the flow. If it's too long, then it will take a lot of cells to mesh it. So again, it's not that good. So I usually choose it to be about a few millimeters. Dimensions, horizontal, sorry, general, and H5, and let's say 3 millimeters. Right here. And this is the throat region, and now the region that we want to draw is the divergent part of the nozzle. So like this and like this. Okay, so now we have to define, so this is the outlet region. And if you remember from the beginning of the presentation, if you read it carefully, there has to be a certain ratio between inlet and outlet. So the outlet has to be 3 or 4 times bigger than the inlet diameter. So since we have here 0.25, this one it can be maximum 1 millimeter. Or the nozzle outlet diameter, the total it will be 2 millimeters. So dimensions again, click on this, click on axis, V6, 1 millimeter. And now let's define the axis, the angle between this divergent part and the axis. We will use again, click on angle, these two, and again I don't like this angle, yes, this one, A7, and again from the beginning of the presentation this angle should be maximum 10 degrees if you want to generate a flat top profile, and I will choose, as always, choose 6 degrees. Alrighty, like this. And now what is remaining is to draw the region outside the nozzle. So this is will be the region from where we will extract the density profile. So this is very important. And again, we go to draw, line. So we can go like this, and again like this to the axis. So when you're on axis, you'll see there a C. And alright, so let's, before anything else, let's give the dimensions here. So this one, V8, will not be very big, so we will want to see the profile, the gas density profile in a region outside here, but don't make it too big because it will take too many cells to mesh the geometry. So I usually choose a few millimeters outside. So in this case, let's say we will choose 3 millimeters or maybe 2 millimeters, like this. And the length of the region outside, again, is for Wakefield accelerators is irrelevant very far away, because the density profile will be Gaussian type, and we don't want that. So the only region where we will have a flat top profile will be very close to the outlet. So a few millimeters, so 2-3 millimeters outside the outlet. So let's say this will be 4 millimeters. H9, 4 millimeters. Okay. And this one we don't have to define it because it's already defined by the rest of the geometry. And now we have to close the geometry. So a line from here to the beginning of the geometry. Like this. And to the beginning. All right, so again, we don't have to define this one since it's defined by the rest of the geometry. All right, so now we have the geometry. And now we have to so this is the next step. We'll define a surface based on this geometry. So we go to concept, surfaces from sketches, and we select this one and generate. And now we have everything that we need to go to the next step, which is to mesh it. You don't have to do anything else. You just close and the program will be automatically updated. So if everything is fine, you'll see there a check mark. What I forgot first is to save the project, so don't do like me. So just give it a name. And save it somewhere. And save it periodically just in case. All right, so the next step, just double click on mesh, and when you double click, the program starts and automatically takes the geometry that you draw, so you don't really have to do anything. All right. So here is the geometry. Again, you can right click and you can see it in different ways. Front, here is not much to see because it's a 2D geometry, but it will be more useful when you have a 3D geometry. And you have here the mesh, and it's very important here. You cannot mesh it with any kind of mesh. For this kind of simulations is critical to have what is called quadrilateral mesh in 2D geometry. This is how it's called, quadrilateral. And for this, right click, insert, and we will have face meshing. Click on this one, and you need to select the geometry. Click on this one and click on the geometry. All right. Okay. So you have one face. And I forgot to do something which is very important. You don't have to close this one. Just go back here and on the geometry, click it and start it. So what I forgot is to measure the distance between this point and the outlet, because in the simulation we'll need to extract lineouts above the outlet, and we need to know the distance between this point and this point. So for that one you will use tools and analysis tools, distance finder, and we will need from this edge. So click here on edge, like here, so it will be here, apply, and next one to a vertex, which is here, so we need to choose vertex here and here, apply. So the distance in the x direction is 17,196 millimeters. So let's write it somewhere, 17.196. Okay, and now we can close it. Since we didn't do any changes, is okay. You don't have to do anything else. Okay, let's go back to meshing. And we have face meshing, and here is the method are like I've told you, quadrilaterals. So what does it mean? Now, without doing anything else, just press generate. Okay, and if you press here mesh, you'll see what does it mean quadrilaterals. So they are squares basically. So the program will start meshing the geometry with as much as possible squares. That is the perfect shape, it's ideal shape. But if it cannot do it, it will distort the square so that it will fit that geometry, as you can see here. This is not an ideal case because the more distorted the square is, the quality, as you call, the quality decreases more and more, and the simulation it's harder and harder to run. It's not much to do about this. If there is the possibility to do the meshing manually, which is much more cumbersome, I prefer to leave to let the program to mesh it properly. And now the number of cells in this mesh is about 54, is way too small. So for supersonic flows, you have in supersonic flows you have a lot of shocks, and if the shock is smaller than the cell size, it will not be seen. It will not be seen in the simulation. It will not be simulated, and the result will be fake. So we will need as many cells as possible. Of course, it's limited by your computer. So if your computer doesn't have enough memory, or the processor is not very good, you don't want millions of cells. But nevertheless, for these nozzles that I showed here, so usually are millimeter size, if you can put about 1 million maximum number of cells, it's a decent number of cells, so it should be enough. If we click on this one and we go to sizing, the easiest way to change the number of cells is just change their sizes. So we go to here element size, so let's say 0.0004. Okay, and generate again. So the number of cells increased. You see here in statistics, again 275. Again, I told you, I told you that we need as many as possible. So we need to decrease the cell size. But before we do that, if you go to quality, and smoothing has to be as high as possible. So to obtain a good quality. And from here, from mesh metric, choose element quality or skewness. So this will tell you the quality of the cells. Skewness will define how much a cell will be distorted. So how much will be different than a square. So let's say skewness, and you'll see here it will give you the skewness on this axis versus number of cells. So these are not very good quality, these are the best quality, as close as possible to 0. It's not a problem, you don't have to worry about this. The program is quite good to generate good quality mesh in general. Okay, so now again, let's reduce, let's say 1. Let's see what happens. Generate. Alrighty, so 3000 again, I don't like it. So you see now the cells, you can use the mouse scroll to zoom and you can see the cells, something like this. So it's clear we need to change this one, so it will be 0. So 0, let's say 5. Generate 12,000, no, 1. So you will see if the number of cells is not high enough, even the simulation will not run, so it will diverge very, very fast. So that is it's a good indicator that you need to increase the number of cells. So I obtained here about 300,000. Yeah, it's fairly decent, it's not too bad. I'm happy with this one. You can increase if you want, but there is no point here to do that. All right, so we don't have to do much now. So in this point, you have to define the inlet, outlet, walls, and so on. So if you go to see the geometry, so something like this. Now if you go here, you can choose edge. So we will choose this edge and right click on it and create named selection, and let's call it pressure inlet. Okay, so you'll see it here. Whatever you named is present here. If you click on it, you will see it points exactly where you define it. Alrighty. The next one, let's choose this, and if you press Control, then you can choose multiple edges and these 3. So right click, again name selection, and let's call it pressure outlet. You'll see it later why I call it exactly like this, pressure outlet. It's the good thing if you name it like this when you import it in Fluent, it automatically recognizes what you want and it will choose the proper settings for you. So that's why it's good to call it like this, pressure outlet. Okay. Now, if you go to pressure outlet, you see 3 edges. So that tells you that you chose the right number of edges to define the outlet. So this is the region outside, which is what we call vacuum. And now click on this one, right click, and let's call it center line. Okay, now the rest of the edges are the walls. You can give them a name, wall, and it will be recognized as wall. And if you don't define it, again, it will be recognized automatically as a wall. If you have to define some extra parameters for each section, then you will call it, let's say, this one, wall 1, wall 2, wall 3, and so on. I don't need that, so it's faster to just ignore it. Okay, so we finished this once. We gave it a name. So let's close it. Okay, we need to wait so that we can go to the next step. Okay. All right. So here you see this lightning sign. That means the mesh has to be updated. So the reason is after we meshed, I gave name to those all those regions, but I didn't update it. So I have to do that. You can do right here. You don't have to open the program again. So right click and update. And the mesh will be updated accordingly. And if everything is fine, you'll see here a check mark. Sometimes if you are doing a mistake or you chose the wrong settings for the meshing, you will see it will not update, it will fail. Or there is another unfortunate situation. Even if it's here shows checked, there is a bug in the program, and when you are going to the next step, when you are trying to import the mesh, it will fail. So it's not a problem with this program. It's a problem with the mesh. So you have to go back and check what did you do wrong with the mesh. All right. So you finish 2 steps, and the next step is to prepare the simulation. So double click on this one. Okay. So here you have the general options, display mesh after reading. If it's a huge mesh, it's not a good idea to display it because it will take a lot of memory, a lot of time. So uncheck this one if that is the case. In this case, it's not a problem, so you can leave it. And here we will run the simulation double precision. Here the number of processes that you want to run in parallel to run the simulation depends on your processor. So if your processor has 10 cores, then it makes sense to put there 10 processes or 9 processes and to leave one core for the rest of the operating system. If you have the version of Ansys Student, that is limited to 4 cores, so you cannot increase it to 5, 6, and whatever. So it's limited to 4. In this case, let's say 4, and you don't have to do anything else. Just start. And the program automatically imports the mesh and here it will check the number of cells, the quality, if there is any problem, and if there is a problem it will be displayed here, and it will give you also the options how to repair it. That is really great. Okay, so this is the mesh that you recognize. Now this signs that tells you that you have there an outlet, and if you zoom on this region, so if you scroll, you'll see again these arrows that will tell you that you have an inlet. So that is really nice to have. It helps you to check if you did everything correctly. Yeah, if you have seen, I moved the geometry, so if you click this one, you can move the geometry around. It doesn't matter, I don't really care about this one. So I go to general scale. Before anything else, let's use millimeters. So I want to see the geometry in millimeters and everything else. So it's easier to have this. Close and check. That checks the mesh. It's good to have this check in case something went wrong. You check it, that tells you the minimum volume. Now keep in mind that when you mesh it, if you expect to have shocks and you want to resolve them, the shocks are usually very small, can be microns. So if the cell is too big, you will not be able to see those shocks. So make sure that the cell size, or the smallest cell size, has a proper size. Okay, if you want to see the report quality, you can press here, and it tells you the quality of the mesh, so aspect ratio. Now if you want to know the definition of each term, check it on the internet. There is a lot of information regarding this. Also the Ansys Fluent documentation will tell you a lot, so check it there. And here the units. Here I will do something different. So the density here is defined in kilograms per cubic meter. I don't want that. So for me, the most relevant unit for density is atoms per cubic centimeter. So to have the conversion factor, you have to use ideal gaseous law and convert from pressure to density. I will not explain here how to do it. There is enough information on the internet, but I already have this conversion factor for helium. So for each gas you will need it. In this case I already calculated somewhere here. So let's see. So no, not here. So it's 0, so this factor is 0.066467 and here the units is multiplied by x 10 to 19 atoms per cubic centimeter. Okay, and close. So each time after that I will check the density, I will have that unit. Okay, so let's start with setting up the simulation. We will use density based right here, and we will use Axisymmetric. Check this one, and you have the option to have a steady simulation or transient simulation. We will not do transient, we will do steady. So that means the simulation is running, is ignoring the time steps, and it's run in big time steps, so that it will reach the point where the parameters of the flow, they don't change anymore. So that means it's a steady state regime. It's a faster way to obtain the result, and this is the suitable for what we want. If you want transient, there is a different discussion there. Probably we will cover in a future tutorial, but right now we will use steady. All right, and we go to model and energy. Now again, I will not explain why I make these choices, but if you want to know, and you should know in detail, what does it mean, you have here a help. So if you click on this one, that will open the documentation for exactly this window. So it will tell you what does it mean, definitions, and so on. So this is valid for every step. So if you choose this one, and for instance this one, if you double click on it, again you'll have a help, and it will give you the details about every part of this of every choice that you have here. As you can see, you can choose many things. So in our case, we will use viscous SSTK omega model, and we will not change any options here. By default, we will keep them as they are. They work. I use them all the time, so you don't really have to worry about them. Okay. All right. So we chose the model, which is viscous K omega. Then we need to choose the materials. In wake field accelerators, most of the time we are using helium or hydrogen. So in this case, we will use helium, and if you go to double click, create edit, Fluent database, and we go down to helium, like this, just copy, close, and close. Okay, so we have helium. Now we have to do something, another choice. So the density here is defined as constant, which is not suitable for our simulation. We will choose ideal gas. But keep in mind that even if you chose ideal gas, the properties of the gas are the real ones. So all of these are are real. If you really want, you can choose instead of ideal gas, real gas, if you know what you are doing. But I've seen there is no change in the result, so I use ideal gas. Press change create and close. All right, and here at solid is chosen by default aluminum, so this defines the wall. It doesn't really matter in our case, since we don't care about the walls. As I've told you, they are considered adiabatic, so there is no heat transfer between the fluid and the wall, so it doesn't really matter the material. But if it matters, again, you can define it. You can put copper or whatever you want. Okay, now cell zone condition. We have to do something. If you forget this one, then it's not good. So by default, the material name is air. So it uses air. You have to choose helium. So helium, apply, close, and click on cell zone conditions and operating conditions. So if the nozzle is surrounded by air, the air at atmospheric pressure, this by default is this value, so approximately 1 bar. We don't want that because our reference is vacuum. So you need to put here 0. Okay. Now the next step is to define the boundary conditions. So we will define the pressure at inlet, pressure at outlet, and the wall temperature and so on. So inlet, double click on it, and this is the total pressure. So in these simulations we will need a very high inlet pressure, because this is how these nozzles work. Otherwise you will not have a high you will not have a flat top profile. So usually the pressures are about 10 bar, 20 bar, 30 bar, and something like this, or 40 bar, depending on what density you want to reach at the outlet. In this case we will use about 20 bar, which is 2 million approximately pascals. So this is 2 million. And here supersonic initial gauge pressure is not very important. It has to be slightly lower than this one. This is just to initialize the flow. You don't have to worry about this one. It's not particularly important. So just 999,000, just slightly smaller. And here we will use intensity and hydraulic diameter. Again, check the definition of this term, how it's defined. So depending on how much turbulence you should expect, you will write here a number. So between 1 and 5 it's fairly decent for our simulations. If much higher if the expected turbulence is higher. 5% is decent. And hydraulic diameter, check how you define it. I will not explain it here. Use help, that's your best friend. So apply, and here you can define the temperature at the inlet. This is the room temperature. I don't change it. All the simulation, because the gas is at the room temperature, so that it doesn't really make sense to change the temperature. But if you really need it, you can change it from here. The rest of the options are not active because of the model we chose. So apply, close. And now at the outlet we need to define the pressure. So here is vacuum, approximately 0.01 pascals. And again, hydraulic diameter 5%, and it doesn't really matter, let's say 3 millimeters. And again, you can define the temperature at the outlet. I keep it by default room temperature, close. And now you can see here center line, so is defined as wall, is wrong. Right click on it and type, and here you have to be careful what you choose. Even if you are tempted to choose symmetry, don't do it, because it's not symmetry. You have to define it as axis. So this defines the axis of rotation of your geometry, because it's axisymmetric. So you choose this one, you'll see it here. You don't have to do anything else. You can see here we didn't define the wall, but it's by the automatically is recognized as a wall whatever we didn't define. So if you want to see it, just display and shows the wall. Sometimes it's good to check to make sure that different boundaries are defined properly. All right, so we don't really have to do here much. Then we go to the next step, methods. Here you don't really have to do anything, so this defines the accuracy of the simulation. So this is quite good. So it's second order upwind. I will not explain what is this, so just check the documentation. So you can choose first order. This is very rough, solution. It's recommended to use second order upwind for all of this. I don't change this. I keep them by default. It always works. All right. So here we don't do any changes. Just check, make sure that is second order upwind. All of this. Controls. Most of the time I don't change this, but sometimes when the simulation is not converging properly, you need to adjust these parameters, especially the current number. So this has to be decreased. Now, so you can put 1, 0.1, 0.01, and so on. Now the drawback is if you decrease this number, the simulation time, it will increase a lot. So decrease it only if you really don't have other option. So if you see that is diverging and no matter what you do, you cannot solve it, remeshing and so on, then decrease this number and rerun the simulation. All right. Now monitors. So we will have here residual. So the residuals by default are 10 to minus 3, is fairly decent. So I prefer to put here 10 to minus 5, so change all of this. You can stop the simulation anytime, so you don't really have to wait until it reaches this this convergence criteria. So you have, you change this, you don't have to do anything, just press OK. And now report files. So now we will need to check during the simulation. So the steady state regime is reached when the density, for instance, doesn't change anymore. But the question is the density where. So it makes sense to have the density at the outlet. So when the density that region doesn't change anymore, that's one of the criteria required to have a converged simulation. So a steady simulation. So here we press new, report file, and we go new, surface report, and we can choose facet maximum, let's say, and here we can choose what parameter we want to monitor, and we will choose density, and where we want to choose is here at the outlet, and we can have report file and plot. We don't really care about file, we just need it to plot it. Okay, and now we need to add it here. Okay, and close. All right, the next step will be initialize. So initializing, it calculates using the roughest approximation possible. So it will calculate the initial values to start the simulation, and those will be refined step by step by the simulation. So these are the initial values. You don't really have to do anything, just use hybrid initialization and initialize, and you'll see here is calculating something. If something is wrong, it will tell you that it doesn't converge, something is not okay, so you need to check what is going on. Here everything is fine, you don't have to do anything. And now comes the we need to draw those lineouts. So we need to know from where we want to extract the data. So we will use, you can do it even after you finish the simulation, but it's better to do it now, because during the simulation you might want to check if everything goes well, how is the profile and so on. So it's easier to do it here. So double click on XY plot, new surface. So now we define the surfaces, isosurface, and we choose mesh. And you have two options here. In the you will draw the surface of constant mesh in X or Y direction. So in our case, we are interested in isosurface in X direction. Here, if you press compute, you will see it, the minimum, which is 0, the inlet, and the maximum, so where is the end of your domain. And you remember earlier when you create the geometry that you measure the distance between the inlet and outlet. So here is very important. It's 17196. So we will use this value. So let's create, so 17196 plus 1, because we want to see 1 millimeter above the nozzle. So 18.196. Is it right? 196, okay. And you can give it here any name. I will call it X1, so that you'll know it's 1 millimeter above the nozzle, and create. All right, and another one, 19, so this is X2, and 20, X3, all right, and the last one, X4. Yeah, if you are trying to create a surface where you don't have geometry, you will have an error here, so it will give you an error. All right, close. And now, since we already have a rough solution, so given by initialization, so if you are choosing density and choose these 4 values of the line outs, sorry, it's easier to do it from here. So setup and plot. Now it looks weird because the other axis is deactivated, so you make sure that is deactivated. So 0 is deactivated, 1 is activated, plot. And now you can see the density profile. Now, if you want to see it from the edge of the nozzle, you deactivate that one and plot. So you see only half, the complete density profile of the nozzle, it goes symmetrically in the other side. So you have it here. This is it. Now, at this point, it's a good idea to save the project. Anyway, when you start the simulation, it will save automatically, but just to be safe. All right, and now let's go to calculation activities. Now you have the option to autosave, which is a very good option. It's a very good idea to save it periodically, especially if you don't supervise your simulation, so you just let it run over the night or something, or unsupervised. And what you can do here, so let's say you want to save every 1000 iterations, and if you press edit, maybe you don't want to keep all the files, so here you can retain the number of files, the previous files, so 1, 2 or 0 or whatever you want. So let's say 2. You can do a lot of stuff here, so you need to check other tutorials and so on, so you can run multiple simulations, for instance, by changing the pressure, for instance, and inlet automatically. So it will change the pressure, run the simulation. When it's finished, again, it takes the next command, run the simulation, save it, and so on. So you can do batch simulations. Right now we are not really interested. Okay, we finished here, and we go to run calculation. Now it's good to check case after you finish setting up the entire simulation. If you forgot something or something is wrong, you will be told here. So check simulation, no recommendation, so everything is fine. Now number of iterations that you want to run, you can put as any number. You can stop the simulation anytime, so you don't really have to worry that if you stop the simulation you will lose the results. So let's say 1 million, and here is the reporting interval, so it will give you a graph of the it will give you the residuals and whatever you monitored. In our case, you monitor the density at the outlet, so it will give you another plot here. So the reporting interval, how every iteration or every 5 iterations and so on, and the same profile update interval. You can keep it 1, it doesn't really matter. All right, now we finished the setting up the simulation. We just press calculate, and now the simulation starts. Here is the density at the outlet. You can see here it's in atoms per cubic centimeter. Here are the residuals. If something goes wrong, it will start to diverge, so it's going up. In that case, you need to check what is why. If it might be the mesh is not fine enough, or the current number is too high. It can happen, actually it happens quite often with supersonic flows. I will give you at some point, I will give you a short video on tricks how to run the simulation in those cases without headache. So now you let the run to simulation until you get convergence. So what does it mean, convergence? You need 3 criteria to meet here. So the residuals, they have to go down to a very, very small value. Some people, they prefer 10 to minus 3. I prefer to let it run until it doesn't change anymore. So it will reach, is going down, 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 and after that it will reach a plateau and doesn't change anymore. That is for me one of the criterion to reach convergence. The second criterion is the parameter, so the density at the outlet in this case doesn't change anymore. So again, reaches a plateau, is going up or down, and at some point doesn't change anymore after running many iterations. So that is another criterion for me, that is we reach the convergence. And the last but not least, so yeah, if I stop the simulation, you can stop it, you don't have to worry about this. So even more, you can stop the simulation and file, save, And you can even change, for instance, the pressure. So if, let's say, you want a different pressure at the inlet or outlet, you can do the now and again press calculate, and it's fine. If you did something wrong and you want to go back, all you have to do is just file and import data, and here is the one that you saved, so you can go back. You don't have to worry about this. Also, it will save automatically how you define it there, so you can always go back in case you want to make to start from a different time. You don't want to start from the very beginning. Sometimes you have to wait days and days for a simulation to finish, and if you do something bad at some point, you will lose the entire simulation if you don't save it properly. All right, and the last criterion for to reach convergence is you need to check the flux, the mass flow rate. So of course you need to have a balance between the amount of gas that is going through the inlet and outlet. If it's not, then you don't have mass the mass is not conserved, so the simulation is wrong. So you check this one with mass flow rate from flux reports. If you press pressure inlet, pressure outlet, and you press compute, you see the difference between inlet and outlet. So normally this one should be, one of these should be positive, one should be negative. So it's clear the simulation has not reached is not anywhere near close to the convergence. So the difference between these ones, which you can check here, has to be about 1% or even less if you really want to have an accurate solution. So always check this. And if you are satisfied with all these three criteria, criteria, then you can stop the simulation, save it, and analyze the data. Again, if you want to check periodically the results, you can go to plots. You can do that and plot like this, and you can see the density profile. Or you can do something like this. So if you go to graphics and contours, setting up, you can show the contours of density, pressure, velocity, so all sorts of parameters depending on what you're interested in. So if I press this one, save display, I can see contours. Now you can contour lines, so something like this. I don't really like to see only half of the geometry. It's especially if you want to present it. So if you go to views and so if you choose these ones, then it will mirror and it shows the entire profile, the entire the entire cross section. So you have it something like this. Another option which is really nice, so if you go to color map options, now here you cannot really see much, but if you plot it in logarithmic scales, which you choose it from here, and let's say 20 colors, so you can see now the flow. You can see you can change a lot of things here, so depending how you want to present your results. Alrighty. And I can press calculate. So if you made some changes and you want to keep them, we didn't really make any changes. We just played with plots and graphs. But if you are making any changes and you want to keep them, you just press this one and that's it. So now you can carry on with your simulation. It's going again and again forward. So yeah, so that is now this is the simulation. When it reaches the convergence, you can stop it, for instance, and close it. So the things that I showed you here, you can see the data, you can plot the data, but if you really want to present it properly, you need to use a different program. So if you close this one, I assume that now I finished the simulation, I'm happy with the convergence and so on. So you have to go to solution. No, sorry, not this one. So this will take the, when you open this one, it will take the last saved result. That's why it's called solution. You are interested in results. So if you open this one, this is CFD post. So this is used to analyze the data. Okay, so here this is the program that you use to extract any results that you want. So this is actually it helps you to organize the data in any way you want, extract, even calculate certain parameters that you are interested in. I will not give details on this one. There are plenty of tutorials on the internet. YouTube is your best friend, so check it there. It's beyond the purpose of this tutorial. So I think this is pretty much it. Now, if you liked my tutorial, please subscribe. And if you have the means, you can support my future videos. Check the description how. Thank you.